Before numbers were standardized, quantity was a matter of arrangement. A watcher would look at a specific pattern of signal fires, one lit, one dark, to understand the count sent from the valley. Ancient record keepers used knots in a cord to achieve the same thing. The count was never the physical string or the knot itself. The count was what the arrangement meant. This distinction remains central to modern computing. The sequence 1010 reads as 1010 in a decimal system, but in binary, that same arrangement represents the number 10. Data constantly arrives wearing different costumes, the base systems or radices of different traditions. To work with these values, a system must be able to look past the digits and identify the specific value underneath. The programming language APL addresses this through a specific glyph, tall, also known as decode. It stands at the border of these numeral systems, reading the faces of incoming data. In this framework, numerals are temporary. The calculation strips away the specific arrangement of digits to find the presence beneath them. The decode function requires two inputs, a radix, which defines the tradition of the costume, and an array of digits dressed in that tradition. To find the value, decode sums the digits, but each is weighted by the power of its position. Starting from the right, each place is worth itself times the base of the system. In a binary system, this means the leftmost 1 is worth 8, while the third digit is worth 2. The function collapses multiplicity into unity. The 4 separate digits of the binary costume disappear, leaving only the single number they represented. This process is universal across bases. In a hexadecimal system, the digits 10 and 15 resolve just as quickly into the value 175. Decode acts as a functional funnel, reducing an array of digits into a single definitive result. But computation often requires the opposite move. Once a value is processed, it may need to be dressed back up in a specific costume to be sent back out into the world. This is handled by top, or encode. It takes a single number and a base, then systematically decomposes that number into an array of digits. When we pass the number 10 through a base 2 encode, the function determines how many times each power of 2 fits, laying the digits out as a binary costume, 1010. This can create issues in large data pipelines. If different numbers are encoded, the resulting arrays often end up as different lengths, making them difficult to compare or align. APL solves this by allowing for a vector base. By providing a specific pattern, like 4 binary positions, encode tailors the output to that exact shape. If a number only requires 3 digits, encode adds a leading 0 to fill the 4th pocket. This ensures that every piece of data is the same length, regardless of its content. This structural discipline allows disparate values to be aligned into a matrix, where they can be read and compared row by row, all at once. It is easy to view decode and encode as two unrelated tools, one reading, one writing. However, APL includes a power operator that can run a function in reverse, essentially finding its mathematical inverse. When we take the decode glyph and apply the inverse operator, we are asking the system to run the recognition process backward. The resulting expression is functionally identical to encode. Running the act of recognition in reverse becomes the act of tailoring. These symbols represent a single mathematical gesture performed in different directions. Recognition and tailoring are two sides of the same crossing. Crossing a threshold out is the same movement as crossing it in. The traveler passes through, only the direction changes. In APL, the distinction between a value and its representation is resolved through this inverse relationship. The numeral is the costume, and the path between the two is a reversible loop.